Welcome to the Contractor School. Remember to take good notes. We're in sections for service load. In this case, the question is a service load, but it's really a service for a recreational vehicle site. So let's go ahead and put this one in our notes and make sure we can get the math on this one. And let's turn to our code book section 551.73, and there's a table as well, 551.73 in our code book. So I got it up here on the board. Hopefully you can see this. I'll try to zoom in a little bit here. There's a table for the service entrance conductors, and that gives us a percentage multiplier, right? This is we're in the section to do math here for this lecture. That's what we need work on here is the math, right? So there's going to be percentage multiplier depending on the number of sites, right? So we're going to have to line up the number of sites with the demand factor for that number of sites, and then do some math, right? But first, before we go to the table, up in here in the paragraph, I'd like for you to highlight the whole paragraph. Just put a box around it. Don't put highlight every line. Just put a box around it, and then in this particular case, the question was that the sites had 20 and 30 amp supply facilities. So down here I see 20 and 30. You might want to highlight that, and then you might want to actually start highlighting right here for it's just 3600. That's actually pretty important, right? The 3600, because the 3600 volt amperes per site will have to be multiplied by the percentage we see in the table for the number of sites that we have. Okay, so in this case, this particular question said that there was 32 sites, right? 32 sites. So now that you have that highlighted, and if you go down here to 32 sites, down here, and you see the range here, 25 to 35, I see a 42. Okay, so there's a couple of pretty important numbers, right, that we need to go ahead and put in our notes, right, to make sure we get this thing down. In this case, there's just like a little formula here, right? So let's go ahead and calculate this thing. And I'm going to go to my notepad. You go to yours, okay? And I'm going to clear this thing out. And I'll start a new page, okay? Because this is we're still talking about a service load, and we'll have a lot of other questions regarding service loads. They hit you pretty hard on that. They'll probably ask you 10 questions on services, okay? So we gotta make sure we hit this thing and how to do the calculations for service or feeders or branch circuit conductors, and make sure we get it done well. So to calculate the load, right? So let's go ahead and put that and since we're talking about a recreational vehicle, right? If we're talking about recreational vehicles, let's go ahead and put RV, right? RV service load, right? And there's a little calculation here, right? Wouldn't it be the number of sites, right? Number of sites times the load, there should be an A, load per site times the derating factor, right? Times the demand, right? That's what the code book calls it, the demand, or what I call the derating, okay? So the number of sites in this case is 32 sites, right? The load we highlighted in our code book as 3600. So times 3600 volt amperes, right? And then times the demand. Let's go back and look at these things, make sure we got it here in our code book. The demand was 42, so there that is. And then also the 3600, make sure we know where that comes from. Why? Because it's 20 and 30 amp circuits. Okay, that's what it's equipped with. So our demand, once again, 3600 is where that comes from, and then the 42 is from down here. Why? Because we've got 32 sites in the RV park. Okay, so I'm going back to our notes here. Would it be times 0.42, right? And then we just bang this thing out, get our calculator out and knock it out, right? Wouldn't it be, pull it up here, 32 times 3600 times 0.42, and I get 48,384. So it's going to put that one in our notes. 48,384. I'm sorry. So write that down. 48,384, and we must be talking about watts or volt amperes, right? It's going to put a box on that one, put a star on it, memorize it, and here's your little procedure right here regarding how to calculate it if the numbers change, and they probably will. I mean, you're going to get this one, but you may get another one because they like RV sites and the calculation for RV sites, as well as some other topics, okay, regarding loads. Okay, and this probably isn't a bad time to go ahead and make sure we we get some other stuff in our notes. This is actually going to be, we're not going to go over these in detail. We'll go over some of them, but I need for you to, this is going to be homework, right? So I'm going to put here homework, right? This is going to be done not at the seminar, but done by you at home, right? These are other brand new sections that are being asked for the 2017 code test. Okay, new sections, right, from the code, right? And they're hitting these sections hard. So what I'd like for you to do is to read and study, and I'll underline that, the word study, these sections, okay? Temporary installations. So number one, let's put in our notes, temp installations. That is section 590 in your code book. Very important. They're asking questions off of there big time. Okay. Number two, electric vehicles. Electric vehicles, right? And also the CFM for those, the ventilation for electric vehicles. Okay. And that's Article 625. Okay. Very important to read that. There's going to be at least 2 or 3 questions on your exam from that section. Okay. Number 3, solar photovoltaic systems. So let's put solar. Kind of abbreviate photo systems. Right, that's Article 690. Right. Brand new questions coming off of there. Okay. And then fire pumps. Like the disconnects for fire pumps, overcurrent protection for fire pumps, and let's put that in our notes. Write this down, and that's Article 695. Okay, so I want you to read, right, and study these sections, not at the class, but at home. But prior to taking your examination, you can have your code book in your truck, right, and you can highlight this section. And read through it, make sure you're comfortable with any of the math that might be involved in here. And also, like I said, overcurrent protection, disconnects, branch circuit conductors, things like that from these particular sections. Okay, so like I said, that's homework. Okay, but going on to more service calculations, I'm going to go ahead and leave that up just for a second here. Once again, temp installations 590, electric vehicles 625, solar systems 690, and then the fire pumps 695. That is homework. Okay, RVs definitely on the exam, and you should already have this in here now, but this correct answer for this one that we calculated for the service of the RV park, 48,384 volt amperes. Okay, so moving on, let's get another page here, and let's go ahead and go to another question. Okay, according to National Electrical Code, use the tables and the articles to solve for the following minimum size. Okay, ground electrical conductor. So we're going to be sizing for a ground electrical conductor and a supplemental electrode bonding conductor. So both, right? So we're doing both ground and electrical conductor, right? That's this one here, right? There's going to be a table for that, and then supplemental electrode bonding. There's a table for that too. Okay, and notice the answers have 2 answers in each question. So there's the size, in this case 1 og for the ground electrical conductor, and then a 6 og for the supplemental electrode bonding, a bonding jumper. Those are two different things. One's an electrode conductor, one's a bond or a jumper, okay? Bonding jumper. So in your code book, there's a couple of sections that we definitely want to highlight. And the first thing to understand is, to size the ground electric conductor is based on the service, right? So to size this ground electric conductor says assume that the service is 400 amps, okay? And it's fed from parallel 3/0 copper conductors in separate wasteways, and the bonding jumper bonds the water pipe to the ground rods. Interesting question, right? Interesting question. So we've got parallel conductors used for the service. They're size 3/0. But this should ring a bell. My service is 400 amps. It's the 400 amp service that dictates the ground electric conductor size. So let's go to that table, okay? And let's look at what size my service conductors must be, okay? Let's go and look at the ampacity here, right? Let's look at the ampacity 400 amps, and let's look it up here as to what size it would be, right? So that we could size. We know it's in parallel here, but in this case, to size it, we need to know the ampacity. Use this table to size it, right? We use this table to size it so we can take it on over to the ground electric conductor table and then size the ground electric conductor. So let's go here first. We'll be going here quite a bit on this lecture series this weekend. Table 31015 B16. As you can imagine, that is one of the most commonly used articles, for this particular examination, since it's an electrical exam, right? And so here's one of the tables that's on the exam. We won't use it in this case. We're going to jump straight to the one that we need. This table here, 31015 B16, formerly table 31016 in older code books, okay? And it's used for not more than 3 current carrying conductors. So if you have more than 3, you got to use the tables behind it. And then if it's a different temperature, you got to use the tables that are behind it as well. There's 2 other smaller tables that we'll be going to shortly that show you how to use this table to derate for number of conductors and a different ambient temperature. But we don't need that for this question. We just need to look up the 400 amps, okay? Now, if we look up the 400 amps, right, and we should be able to see that it lines up with a 600 kc mill. So down here, 400 amps, right? And we're going to go ahead and assume, right, that we're going to use 75-degree terminations. By the way, that is something that you should really just circle big time. Put a big old circle around this because you want to default here. Now, if you're given NM, you might want to write NM up here for non-metallic sheath cable. Right above the UF, you should write that in there. But THW insulation, THWN insulation, and even if it's not, if there's not a temperature given or an insulation given, for the ampacity, default to this column. So I want you to put a box around this thing big time because that's easy to forget. The other thing with motors, you always default here as well. Okay, so this third column here is if they give you a question using THHN. So you could come here, but not as often, to the third column. That's based on 90 degrees Celsius conductors. Your terminations are usually 75 in general. So you're going to default to column number 2. Come on down. See C400, and I see 420, right? And then we'd slide on over. After you see the 420 there, you'd slide over to this side, see the 600 kc mill right there. So that would be the size of the service. Now we're going to use that size of the service to size the grounding electroconductor. Okay, so in our notes, let's put here for 400 amps, right? So for a 400 amp service, right, you'd need 600 kc mill conductors, right, based on table 31015 B16, right? So that's step number 1, right? We need that, right? Now we're going to take that number on over to table. Where are we going here? We're doing ground electric conductor. Let's double check. Yes, ground electric conductor. So that's the first thing we're going to do, ground electric conductor. So that's going to be table 25066. I'm going to turn there in my code book. You turn there in yours. We just got to back up a little bit, right? If you got tabs, which you already should have tabs on your book. If you don't, you need to get tabs. They're only like $15 on the internet, okay? Or on Amazon, they come in the next day, but you need tabs because it speeds you up. If you're still looking for this table, you're too slow, right? I mean, we should be able to get to these tables fast because we have tabs on them, okay? So we need table 250, 66, right? And don't we need to go down to this little section right here? Why? Because it says through 600, doesn't it? Over 350 kc mil for the service, right? This is the service size, and this gives you your ground electric conductor size, right? So it's the service on the left that dictates the ground electric conductor on the right, okay? And default to copper in general, unless they tell you aluminum. It's always copper to copper, never aluminum to aluminum. That's going to be kind of weird. We don't use the aluminum columns that much. If you find yourself in that column, you're going to be making a mistake. Matter of fact, it makes good sense actually to put a gentle line through here, kind of mark it out so you don't accidentally use it. Or you could put a box around this section and a box around that section, and that way it highlights the section that you're going to need 99.9% of the time. Okay, so in this case, we got 600, which would fit right in there, and we followed on over till we see what? A 1/0, right? A 1/0 copper right there. Okay, we just line the two up, line up the copper column with the 600 kc mil row, and we get a 1/0 og. Okay, so check it out. That's the only one. Now everything else has 6 og, 6 og, 6 og over here, right? So that's the answer, to the bonding jumper. But the real question was, okay, what's the size of the electrode conductor? And the answer is going to be number 1. We know that. Okay, so let's go ahead and put that in our notes, right? Is table 250, 66, right? And we found a 1/0 og, right? That was for the electrode conductor, and that's one answer, right? That's just one answer, right? Now the question is the bonding jumper, right? The bonding jumper. Now there is actually an article reference for this, okay? Then there's also a table that can be used, and so we just want to be careful here. First of all, I want to go to the table. The table, let's go take a quick peek at it, okay? And it's table 250 102 C1, and a lot of people don't even know this one exists. But it's not tricky to find. Again, if you had it highlighted, and it's kind of a cool little table, right? Go ahead and box around it here. But it gives you the bonding jumper size based on the size of the parallel conductors. It's not too tough, right? So if we have, let's say for example, two 400 kc mils, right, and they're in parallel. 400 is not a number in here, but it's over 350 through 600. Well, if we only had one, it would be over here, but since we have two of them in parallel, when we add the 400 and the 400, it would be 800, and we come over and get a 2/0. Okay, so that's kind of how I use this table if it's parallel conductors, right? We just add up the kc mils, or add up the og and double it up, right? Double up the area of the conductor, get the right row, and slide on over. Okay, now in this case, we don't use this table this time. Okay, we could, but we don't need to this time. It makes more sense to use the article reference. Now it actually would fall in and be correct, because you would get 1/0 og here, right, and you'd fall on over to a 6. And you say, okay, well that's the correct answer, but it's actually best to use the article in this case, because and I want to go there now. 250-53E. Why? Because it's a supplemental electrode bonding connection, and I kind of like making sure we get this in our notes, because this article is confused and people don't know it exists. 250-53E is where we're going. 250-53E. Let's go ahead and go there in our code books, please. Okay, computer, it'll probably take me a little longer to find it than you. There it is. Okay, so this one here looks like I'm on page 113. Okay, page 113, and 250-53 is for ground and electrode system installation. and we see supplemental electrode required supplement. So it's required, right? Because we're bonding a couple things together here, and here's are the issues, right? Where are we at here? Where's E? There's E right there. Supplemental electrical bonding connection size. So the size of it, okay, right here. We'll see if I can kind of blow that up a little bit. Says where the supplemental electrical is a rod, pipe, or plate electrode, that portion of the bonding jumper that is the sole connection for the supplemental grounding electrode shall not be required to be larger than 6 Aug copper. Okay, and so there's the answer, right? There's the answer. Shall not be required to be larger than 6 Aug, right? Shall not be required to be larger than 6 Aug. And the question said, to solve for the supplemental bond electric conductor. That's how we know that that's the best article, right? So 6 Aug right there, correct answer number 1. Okay, very good. Okay, so let's go ahead and put in our notes, right? For the supplemental electrode, for the supplemental electrode conductor, right? We were in article 250.53, write this in your notes, E, right? And we found that it was a 6 Aug copper. So let's go and put that 6 Aug in our notes, put a box around it, right? And there's the 2 portions of that question. The 1 Aug for the ground electric conductor, and then 6 Aug for your supplemental electrode conductor. That's kind of a 2-part question. Okay, so let's go ahead and go on. If we could, I'm just going to clear this out. And let's take one more quick peek at that question before we go ahead and move on to a little bit more math, okay? And so there's, as you can imagine, a lot of math on these exams nowadays, getting more and more, so we want to just make sure we work it, and we get comfortable with the math. Okay, so moving on. If a listed resistance type instantaneous water heater or steam boiler is a feeder load of 144,000 watts and is operating on 480 volt three-phase. I always kind of rings a bell for me. How many individual dedicated branch circuits would be required for this appliance? Okay, so now we're looking at how many circuits are required. They're starting to ask this question quite a bit. In other words, how many circuits are required? It's a good question, right? How many circuits do I need for a particular load? That's actually a pretty good question. So we're going to go ahead and go through the math on that one and make sure we can get it get it in our notes, okay? So on that one, let me go back to my notepad, you go back to yours, and let's put this one down in our notes, okay? So the thing about the resistance type instantaneous water heater, this is actually an article reference for that. Since it's an appliance, and those of you who've been studying probably know that appliance is on 422, right? So 422.11, 422.11 F as in Frank 3, and that's going to be for the water heater. Okay, so let's go ahead and go over there. Let's put this in our notes first, right? For the water heater, and there's going to be a little calculation there, right? There's going to be a little indication of how to do this thing. Okay, so for the water heater, so 422.11. Let's go ahead and go there. You go there in yours, I'll go there in mine. Take the time to do this. Turn there in your code books. Don't just watch the lecture. You need to participate here. Make sure we get it. 422.11F. And then 3. Way down here. I'm on the towards the bottom of page 277. Water heaters and steam boilers. Boom. There it is. And there it is, right? The resistance type emergent electric water elements shall be permitted to be subdivided into circuits not exceeding 120 amps. That's what we needed. We needed that portion because we need to know that to figure out how many circuits are required. if we can have 120 amps per circuit, then we need to know that, okay? So we just need a little bit of Ohm's law here. We just need a little bit of Ohm's law, okay? So if that's the case, right, let's go ahead and go to our notepad now, right? And if we know we can have 120 amps per circuit, right, according to the code reference we just read, that's an important piece of our puzzle here, 120 amps per circuit, okay? So when we need to use Ohm's law, we talked about Ohm's law previously, so we should be pretty good at this now, right? I is equal to P divided by E, right? However, remember the question said that it is three-phase, right? We haven't done one of these yet, so let's pay attention here, wake up, right? Three-phase, since it's three-phase, right, we got a bit of a problem. Don't we need the square root of 3 down here, right? 1.732, right? If we forget that, we're done. We're out of there. We can't solve it. We get it wrong, okay? So the total power was 144,000 watts, right? Or 144, this is also 144 kW, right? We already talked about in the previous lecture. 144,000 watts. Now divided by the voltage 480, and everyone always forgets this, times our square root of 3 here, right? This is the square root of 3 over here, 1.732. And we need to divide this two numbers, 144,000 watts, by whatever we come up with our calculator here when we multiply those two, okay? Not difficult to do, but easy to forget, okay? So we got 480 times 1.732, and you get 831. That's nothing you need to memorize, but you do need it, right? The 831.36. 831.36. Now we got to divide those two and kind of finish this thing up here. So the 144,000, just a basic calculator, basic math, divided by 831.36 equals 173.2. 173.2 amperes. Okay. Now, the number of circuits, right, wouldn't be equal to the total 173.2 amperes, right, divided by what we got up in here. Remember, we had to go to this article reference, make sure we got that first, divided by up here at the top, right, the 120 amps per circuit, right? So when we just divide by 120 amps, right, and then we get some number. And it's not going to be an even number, it's going to be kind of a dumb number, right? 173.2 divided by, still in our calculator, 120, and we get 1.44. Well, you can't go over there to Granger or Elliott or Locke or wherever you get your stuff at, right, and get 1.44 circuits, right? You know, doesn't this need to be rounded? Don't you need to size up, right? Size up to 2 circuits. 2 circuits, right? So I hope that makes sense. Once again, the article reference first to get the amount of ampacity we could have on one circuit, okay, and then use Ohm's law. I is equal to P over E times the square root of 3. And remember, you guys, that comes from the workbook. This is something that I think is very important. I'm going to pull up the workbook once again on page 6 and show it to you once again. See, this formula's got to be memorized. You got to write that in your code book. Write it on the back of your arm, or on the bill of your cap, or put a tattoo. But you need this one really bad. Okay, you cannot forget this one. You'll miss some questions. Okay, so once again, that's where that square root of 3 comes from. I is equal to P over E times square root of 3. Multiply it all out, right, to get the bottom. 480 times the 1.7. Get the 831. Divide the two numbers. Power divided by the voltage gives 173. And then your 173 here divided by 120 gives 1.44, size up to 2 circuits. Okay, so I appreciate your time. Thank you very much.